We're going to talk here about opening the I/O gates and basically enabling trusted I/O with confidential containers. And we're going to have a look at this from both sides of the link, from the device side, and this is what Jiewen Yao is going to be presenting, and I'm going to talk about the host side of things. So first of all, a quick reminder. Maybe not so much of a reminder for people that are not familiar with confidential containers, but basically confidential containers is illustrated by this set of diagrams here, where we are running a Kubernetes pod inside a TE VM, a TDX, an SGX enclave, TDX VM, an SCV VM, any kind of a trusted VM, and well, this is the current picture. This is the current architecture, and you can see that part of those boxes are trusted, and some of them are not trusted. And one of the things that are not trusted here, aside from the software pieces, which like the VMM or the Kata containers and the Kubernetes stack, one of them is or are devices. So this red box here with what looks like a NIC, those are not trusted. And to keep the trusted VM safe and trustworthy, we basically cannot do this. We cannot safely directly assign a device into a confidential containers today. And the whole reason for this talk to come up is to move from this situation to this one, where we'd be in a situation where we'd be able to trust the device and basically allow it to extend the TEVM TCP with that device. So what is it that we're trying to protect us from? What is the threat model? So two things to keep in mind. In regular platforms, the devices are owned by a set of untrusted software components on the host. So devices are managed and owned by the kernel, typically Linux kernel, or the VMM, KVM, QEMU. And if you want to take those untrusted host software stack owned devices and attach them to your trusted VM, then you basically are saying that you're going to let those devices, allow those devices to get direct access to confidential memory. Your trusted virtual machine, your TE virtual machine are running off confidential memory. And when you assign those devices that are managed by untrusted part of the software stack, you basically give them direct access to confidential memory. So what we're trying to protect us from or rather said, what we're trying to protect is the confidential memory, the TEVM confidential memory, and we're trying to protect it from the assigned devices, first of all. The IO devices that we're going to assign in the trusted VM are going to be able to DMA into and from the TEVM memory. So we want to make sure that those devices are trustworthy and they can do those DMA operations. We are protecting the TVM confidential memory also from the untrusted host software. As I said, the host controls the platform resources, including those devices that we attach to the TVM. And as such, they could use the devices that are being attached as proxies into accessing the confidential memory. And last but not least, we by attaching a device into a trusted VM, a confidential VM, we add an additional physical link between the TVM and the device, and we need to protect that link from physical attacks. So really, the threat model that we're trying to address with trusted IO is basically protecting the TVM confidential memory from those three kind of vectors and adversaries. So what are the requirements to do that? What should we do to implement and implement that threat model? So first of all, we need to be able to authenticate and verify the devices that we want to assign to a TVM. And by we, I mean the guest owner, basically the workload owner and the trusted part, which is the trusted security manager, should be able to authenticate and verify the devices that are being assigned and offered by the untrusted part of the software stack, which are the VMM and the host kernel. Once we would do that, once we have verified that the devices are trustworthy, we want to protect those trusted devices against the untrusted host software. If we assign, as I said, if we assign those devices into TVMs, into confidential VMs, we want to make sure that the untrusted host software stack cannot use those devices as proxies into accessing the confidential memory. And finally, the requirement for doing trusted I/O is to protect the physical link between the confidential VM and the assigned devices. So to do that, to implement those requirements and to address the threat model that I just described, we are going to use a framework called TEIO. And this is basically a framework that's designed for safely adding and removing devices into and from confidential VMs. And it's a framework. It's a framework that's defined as a set of related specifications. So mostly SPDM, IDE and TDISP, and the two last ones are PCIe specifications. When you combine them together, you basically get the TEIO framework defined. And by adding and removing devices here, what we really are talking about are PCIe devices. So NICs, GPUs, accelerators, and so on. And just to make sure that we're everyone on the same page and aligned, we're talking about direct physical assignment, high performance I/O. We're not talking about power virtualized I/O, like PertIO, for example. And in that architecture with TEIO, we really giving the devices direct access to the confidential memory that's been assigned to the TVMs. Okay, so what does TEIO provide? Through the specification that I described, and if you implement the specification from the host side and from the device side, you basically are able to establish a trust relationship between the device that you want to assign to a TVM and the workload. So to do that, TEIO, the TEIO framework through a secured SPDM allows for authenticating, verifying, and the testing to the device trustworthiness. Once you have done that, once you are able to say, yes, this is a device that is trustworthy, you want to go to the next step. And this is implemented through the PCIe IDE, the integrity and data encryption specification, to secure the physical link that you now have created between the untrusted host and the device. And last but not least, you want to make sure that you can attach and detach the device to and from the TVM in a secure fashion. And this is implemented and described and defined by a protocol called TDISP, Trusted Device Interface Security Protocol. So some of those protocol and specification are currently being defined, currently being ratified, currently being reviewed. So this is something that's being put together into the TEIO framework. So before going into more details on how we want to support the TEIO framework from confidential containers to be able to assign IO devices into Kubernetes confidential pods, let's have a quick view on how the whole TEIO framework works. So on one side here, you have the CPU running the OS or the VMM. You have the trusted security manager. And on top of this, you have a TVM, a TE virtual machine. And on the hardware side of things, you have a combination of a device that is managed by a device security manager, the DSM. And typically, the device would be split into multiple functions, virtual functions and physical functions through, for example, SRIOV. And then you have a translation agent, also called IOMMU or SMMU, for translating IO virtual addresses into physical addresses of your CPU address space. The first thing you want to do is from the TSM, which is a trusted component, a trusted software component running on the CPU, you want to establish a secure SPDM session between the TSM and the DSM, which is the security manager running on the device. So at the end of this SPDM session establishment, both the TSM and the DSM have exchanged keys, and now they have an encrypted secure session going through the untrusted VMM. So they typically use the VMM as a proxy for carrying those messages on the SPDM link. But since this SPDM is encrypted and only the DSM and the TSM have exchanged the keys, the VMM cannot tamper with or modify the package, the SPDM messages that are going through it. So you establish this secure SPDM session, and then the next step is to use this secured SPDM session to secure the physical link between the PCI root ports and the device itself. And for that, you use IDE, which is the integrity and encryption of the PCI link. And basically, IDE goes over the secure SPDM session and allows for the TSM and the DSM to establish and exchange keys for this physical link to be encrypted as well. And last but not least, you established a TDISP session, again over the secured SPDM session. And TDISP allows for now assigning a precise function, a virtual function, on the device into the TVM itself. So the TSM established the TDISP session, and then the TVM and the TSM can use this TDISP session to lock a device, a virtual function within the device, and prevent the host untrusted software stack to actually modify and tamper with this device. So once it's locked, once this function is locked, the VMM cannot change it, cannot reconfigure it without the TSM and the TVM being notified about it and being basically securely unattached from it. Once you have this TDISP session going on, you can optionally, it's not mandatory, but you can have the TVM with basically your workload running a remote attestation and basically getting the measurement from the device and making sure that those measurements are trustworthy and being able to authenticate, verify, and attest to the device trustworthiness by talking to a relying party and verifying the device measurement status and overall security posture. Once you do that, the last thing you do as a workload owner, as the TVM, as the confidential VM, you're gonna let the TSM know that you accept the device. And once you accept the device, you can go through the last steps, which is basically to be able to run trusted MMIO and DMA between the device, between the virtual function that's assigned to the TVM and the TVM itself. Okay, so that's a quick overview of TEIO, of the framework. And now I want to finish this presentation by explaining how we are going to implement this with confidential containers. So with confidential containers, as I said, we're running Kubernetes pod into dedicated TEVM, confidential VMs. And this is the current picture without being able to do trusted IO. And what we're going to add to this picture is a trusted device manager running in the guest in the TEVM. That's going to handle the device assignment, the trusted device assignment. And when assigning a device into a confidential containers pod, we are basically going to have the trusted device manager asking for the device certificate, also asking for the device measurement. And this is happening after the SPDM session is established, after the IDE link is established, and after the TDISP session is established. So at that point, the device that's being assigned to the confidential containers is locked and is not reconfigurable or manageable anymore by the VMM. The trusted device manager running inside the confidential VM, inside the confidential containers that's running the Kubernetes pod, gets the certificate of the device, so it can verify the identity of the device, and it gets the measurements of the device. So it can talk now to with the attestation agent with those measurements that represents the evidence of the device TCB, and talk to the attestation agent that is an already existing part of confidential container stack to actually verify those measurements and make sure that the device is running a set of software stack and hardware posture, security posture that is trustworthy. Once it does that, it can accept the device, and this is when we can safely now assign the device into the Kubernetes pod through a trustworthy link going from the device directly into the trusty VM memory, and something that is usable directly by the Kubernetes pod, which is a direct assignment.